Okay, unfortunately the recording for this morning did not survive, so this is going to be a very fast 20-minute, hopefully less because I have to go to a thesis defense, summary of what we did today. So we started with moment generating functions. So for always, x is going to be a random variable. We're going to assume its moment generating function exists in some neighborhood of the origin. So we'll assume there's some delta greater than 0 such that mx of t exists. And remember, this is the expected value of e to the tx. This is the same as integrating from minus infinity to infinity, e to the tx times the density of x dx. And this is the same as the generating function at e to the t. So what we're really doing is we're taking s to be e to the t. So the reason that this is such an important observation is that all of our results on generating functions follow immediately from moment generating functions under this change of variable. So one of the big theorems is the following three properties. So the first is the following, that the moment generating function of x has the following Taylor series expansion. It's the sum, n goes from 0 to infinity, of mu n prime t to the n over n factorial, where mu n prime is the nth-centered moment. And one proof we did in class on Friday was we said e to the u is the sum of u to the n over n factorial, and the sum of the integral is the integral of the sum. And so what this allowed us to do is we took the expansion for e to the u, put it in here, and expanded. The second proof, proof 2, is to differentiate n times. So if we take the nth derivative, and what we want to do now is we want to pass the differentiation inside the integration. Well, if we pass the differentiation inside the exponential, inside the integral, we want to take the derivative of this with respect to t n times. So it should be the following. So it'll be the integral from minus infinity to infinity of d n dtn of e to the t x fx of x dx. And the reason I can write it like this is because there's no t dependency here. This is a constant, so the derivative of the product is really just the derivative of the first piece. Well, if I take n derivatives, the derivative of this is going to be x each time, so I'm going to get an x to the n, and then a e to the tx. And then what we'll do is we'll set t equal to 0, and when we set t equal to 0, this piece here goes to 1, and we're left with the integral of x to the n times the density. That's our definition of the moment. So the real difficulty is justifying the interchange of the integration and the differentiation. So it's not always the case that these interchanges are possible. So here's a really good warning. I'm going to do this a little bit faster than we did in class. Let's let fn of x be the following. It's going to be n minus n times x minus 1 over 2n if x minus 1 over 2n is less than 1 over n and 0 otherwise. So if you plot this function, here's 0, here's 1 over n, here's 2 over, 1 over 2n, 2 over 2n, 3 over 2n. The function is going to be a triangle function like this. It's going to go up to a height of n. And the reason this function is nice is the area under the triangle is always going to be 1. The base is 1 over 2n, the height is n. If I fix x, I can look at the limit as n goes to infinity of fn of x. So I will skip all the Red Sox jokes and everything. Their defense last night was a joke. And if I choose some x over here, if I choose n sufficiently large, then it's going to be to the right of the triangle, and then all of the fn's at that point will be 0 from some point onward. So maybe my x is here initially, maybe then as I increase n, it comes into a triangle, and then eventually it'll be beyond that because n is going to 0. The only point I have to be careful about is if I chose x equals 0. Well, this is why I started it off like this, because, I'm sorry, wait a minute, over here, I think I just want to go to 1 over n. Right, because I want the base to be 2 over n. Yes, sorry. So sadly, I don't have time to redo this because the actual numbers don't matter, but I think this is what I want, because now the base is 2 over n, the height is n, and I've got a factor of 1/2. Yes. So if I choose the origin as my x, well, as I let n go to infinity, it's never in one of these triangular regions, because I always start at 1 over n. So all fn of 0 is always 0. So the pointwise limit is 0. Why is this dangerous? Well, if I look at the limit as n goes to infinity of the integral from minus infinity to infinity of fn of x dx, and I look at the integral from minus infinity to infinity of the limit as n goes to infinity of fn of x dx, each of these integrals is 1, so the limit of 1 is 1, but the limit here is 0 and the integral of 0 is 0. So the limit of the integral is not the limit of the integral. This is why real analysis is such a difficult subject. Now what goes wrong here, if you think back to Fubini's theorem from Calc 3, the problem is I have an infinity. The function is becoming unbounded over a very small region. What you'd like to do when you do Riemann integration, you have your Riemann sums, you would like to say, well, if I have a small little interval, I can basically throw away the contribution from that. Here, it's those small intervals where most of the action is happening. So the problem is the unboundedness. So the real danger is functions like this, is that a lot of our limits, a lot of the arguments we want to do not hold. The solution is to take real analysis to figure out techniques to handle when are these interchanges permissible. When can I say the integral of a limit is the limit of the integral? When can I say the derivative of the integral is the integral of the derivative? The other approach is to use complex analysis. Complex analysis is far more restrictive than real analysis. There's a lot of functions it does not allow you to look at, but the functions it allows you to look at, they all have nice properties. All right, so a lot of today was spent talking about the glories of complex analysis. In the interest of space, I will skip it. The next property was standardization. If we let y equal ax plus b for some constants, then the moment generating function of y is equal to e to the tb, the moment generating function of x evaluated at at. And the proof of this is very straightforward algebra. The moment generating function y of t, so proof, is just the expected value of e to the t ax plus b. Well, now we do some multiplication. This is e to the atx, e to the tb. Well, e to the tb is a constant. I can pull that outside the expectation. That's the first part of the theorem. And now we have the expected value of e to the atx. And we're going to see a trick that we're going to encounter again and again and again. This is the moment generating function of x, but not evaluated at the point t, but evaluated at the point at. And so all I'm doing here is if I go back here, I replace t with at. So we're left with e to the tb, moment generating function of at. And I apologize that we're going so fast, but this is my second time today. All right, so that's the second one. The last one is the moment generating function of a sum is the product of the moment generating functions. And so this is extremely important. So theorem, the moment generating function of x1 plus xn of t is the product, k goes from 1 to n, of the moment generating function of xk of t. And again, for all of these, I'm always assuming independence. I'm assuming the moment generating functions exist at least in some neighborhood. We actually don't have to prove it again. We did for generating functions. And so all we have to do now is let s equal e to the t, and that proof immediately follows. All right, so these are some of the standard properties we need of moment generating functions. The key part over here in the moment generating function is that if x and y are linearly related, the moment generating functions are very nicely related. And this shouldn't be too surprising. If you think about Celsius and Fahrenheit, if I know what's going on in one, I should know what's going on in the other without too much trouble. All right, so now let's do some calculations and evaluate moment generating functions. This might be in a slightly different order than was done earlier today. So the first is the Poisson example. So this means the probability that x takes on the value n is e to the minus lambda, lambda to the n over n factorial. N is a non-negative integer. Lambda is greater than 0. So the moment generating function is going to be the expected value of e to the tx. So all of these problems start the same. They always start by saying, what is the definition? And once you have the definition, then you start working with that. I'm doing it in my office. I'm not quite sure how the camera swivels. All right, so this is going to be the sum. N goes from 0 to infinity of e to the tn, e to the minus lambda, lambda to the n divided by n factorial. Well, whenever you see algebra, you want to think, what's the best way to handle it? We can pull the e to the minus lambda outside. We have a sum, n goes from 0 to infinity. We have an n factorial downstairs, and we have an e to the tn lambda to the n. Well, if you think about what e to the tn is, this is the same as e to the t raised to the nth power. So this is the same as e to the minus lambda sum, n goes from 0 to infinity, of e to the t lambda to the n over n factorial. Well, this is the definition of the exponential. Recall that e to the u is the sum, n goes from 0 to infinity, of u to the n over n factorial. We're just letting u be et times lambda. So this is going to be e to the minus lambda e to the t to the lambda, which is e to the negative, well, we'll do it this way, e to the lambda e to the t minus 1. And because this is sometimes hard to view, sometimes we'll just write x for the first one and then do lambda e to the t minus 1 to just make it a little bit easier to view what's going on. Now that we have the moment generating function of the Poisson, we can calculate the moments by just taking derivatives and setting t equals 0. What I particularly like about this is the moment generating function is very nice, and it involves what looks like a really painful problem from Calc 2. Where you get a lot of these busy work problems where whoever cares about these problems, usually no one, the teachers are just trying to make sure you understand how to apply the rules of differentiation or integration. Why would you do an exponential of an exponential? Great way to test a chain rule. But here we now see a reason why we would care. So the mean, mu, would just be the derivative of the moment generating function at 0, and then the second moment would just be take two derivatives at 0. So we would just differentiate this. Once, twice, set t equal to 0. This is now Calc 1. I no longer have to do this. I trust you to do the calculus at home. What I want to do is I want to show you how you can do this with Taylor series. So e to the t minus 1 is going to be t plus t squared over 2 factorial plus t cubed over 3 factorial plus dot dot dot. So if I look at e to the t minus 1, this is going to be, I can pull out a t, and so now I get the moment generating function at t is going to be exponential of lambda t, I'll pull out a t, and I've got a 1 plus t over 2 factorial, how about 2 factorial, plus t squared over 3 factorial plus dot dot dot. And now I can use my series expansion for the exponential again, and I get that this is equal to 1 plus lambda t, and this whole piece here, 1 plus t over 2 factorial plus dot dot dot, plus, now I'm going to have the squared term, the u squared term, so it's going to be lambda squared t squared 1 plus t over 2 plus dot 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 squared over 2 factorial plus dot dot dot. So in terms of which higher order terms matter, the next terms here will involve a t cubed. So if I only care about the first two moments, they're not going to matter. That's what's so nice about having e to the t minus 1 is the constant term is cancelled. So as I go higher and higher, u to the n is going to start off with a t to the n. So if I now regroup, I get 1. The linear term is just going to come from here, plus lambda t. The t squared term, I'm going to get a lambda t, t over 2 factorial is a lambda t squared over 2. And here I'll have a lambda squared t squared over 2 to get a lambda squared plus lambda over 2 factorial t squared. And you can see here's the first moment, here's the second moment, lambda squared plus lambda. If I now want to find the variance, I would subtract off from the second moment the square of the mean, and you would see that the variance is going to just be lambda. The standard deviation is square root of lambda. So the variance of x will be lambda. The other thing that's really nice about the moment generating function is you see the factorials here are exactly what we want. Because it's the series expansion is the sum of mu n over n factorial. And so here we've got the n factorials already. All right, so this is the Poisson random variable. We're going to have a lot of stuff with the standard normal, so as long as we're doing examples, let's do the standard normal right now. Now you might say, of course, that we might need to look at not just the standard normal, but all normal distributions. What's nice is we've talked about properties of the moment generating functions. If I know x and y is linearly related, I know the moment generating function of y. And so it's enough to do x is normal 0, 1, we can now pass from our laws to any other normal. So we want the moment generating function of the standard normal. It's going to be the expected value is always definition, e to the tx. So it's the integral from minus infinity to infinity, e to the tx, 1 over square root of 2 pi, e to the negative x squared over 2 dx. And again, the standard normal just makes the algebra a little bit cleaner. We complete the square. We have the two exponentials. We want to combine them. We have a 1 over square root of 2 pi. We have an e to the negative 1/2 x squared minus 2 tx, because I have to have a 1/2 here. And now you can see that this looks a lot like a square. It looks like x minus t. So what I want to do is I want to put in a t squared and then subtract a t squared. So I haven't changed anything. I've added 0. So we added 0 in a very good way. What's nice about this, we pull out a t squared, the minus and the minus reinforce, and we get an e to the t squared over 2, integrate from minus infinity to infinity of 1 over square root of 2 pi, e to the negative x minus t squared over 2 dx. And you see, this is the density of something that's normal with mean t and variance 1. And so one of my favorite tricks of integration for probability is to always convert whatever problem I have to integrating a probability density function. And if we integrate a probability density function, we know the integral has to be 1. So this is now 1, and we get the moment generating function is e to the t squared over 2. It's actually more convenient to know that the log of the moment generating function is equal to t squared over 2, and the moment generating function is the exponential of t squared over 2. And the reason is we're going to be dealing with sums of independent random variables. The moment generating function of a sum is the product of the moment generating functions. We don't like products, we like sums. We take a log of the moment generating functions, and now we'll have a sum of the log of the moment generating functions. So the goal is to show not that it converges to the moment generating function of the normal, but the logarithm of the moment generating function. More generally, if we let y be normal with mean mu and variance sigma squared, then the moment generating function of y is going to be e to the mu t, e to the sigma squared t squared over 2. Okay, so this is the moment generating function of the normal. All right. Now, in the discrete case, we saw that the moment generating function, or the generating function, was enough to uniquely determine the density of a discrete random variable. It is unfortunately not the case in general. So a bad pair is the following. Let's let f1 of x be 1 over square root of 2 pi x squared, e to the negative log squared x over 2. Let's let f2 of x be f1 of x times 1 plus the sine of 2 pi log of x. And for both, we'll say x is greater than 0, and the densities will be 0 otherwise. And so I believe I've got them written down correctly over here. If not, I'm running out of time because I'm about to go to colloquium. Yes. So you'll notice that the sign is going to be a little bit periodic. It'll oscillate. This quantity here will always be between 0 and 2. So the two conditions we need to check for these to be probability densities are non-negative, yes. As an exercise, integrate to 1. If you plot them, f1 of x looks like this, and f2 of x is oscillating around it. I guess this one should go all the way down. And every now and then, when the sign is 0, it's going to be exactly equal. Sometimes it'll be twice as high, sometimes it'll be 0. These two densities have the same moments. So what this tells us is that knowing the moments is not enough to determine the densities. So there are two big theorems we need from complex analysis that will allow us to handle situations like this. So the big theorems are the following. And in both of these cases, I'm always going to assume all moment generating functions exist and converge if the absolute value of t is less than delta for some delta greater than 0. So the first is theorem 20.4.3, which says if we have mx of t equals my of t, so the moment generating functions exist in some interval, this implies the cumulative distribution function of x equals the cumulative distribution function of y. And of course, then that immediately implies the density of x equals the density of y, because the densities are just coming from differentiation. So that's the first result. The second result we need is theorem 20.4.4. And in this case, we have a sequence of moment generating functions that converge to the moment generating function of x. X is a fixed random variable. It has a CDF f of x. It has a moment generating function which exists. Then the result is, if we have this kind of convergence, there exists a unique, so this means there is a unique CDF f, which turns out to be f of x, such that f is determined by x, we've got that there, such that if f is continuous at x, then the limit of f xi of x equals fx of x. So in all places where the CDF is continuous, if the moment generating functions converge, then the cumulative distribution functions converge at that point. All right. The last thing that we talked about today was briefly stable distributions. So sums of normal are normal. Sums of Poisson are Poisson. The parameters might change a little bit. So we're going to talk about Cauchy very quickly. So we'll say x is Cauchy AB if the density is some normalization constant 1 over a squared plus x minus b squared. A does not equal 0. B is any real number. The nice thing about writing it as a squared is I don't have to worry about a being negative and things not being defined. So this is a Cauchy distribution. We've talked many times about how if we have a sum of two Cauchys, it's Cauchy. But the question is, which Cauchy? So maybe this has parameters. We'll take a1 and b equals 0. This will be a2 and b equals 0. And then what's a, what's b? Well, if we wanted to solve it, it would be in the special case when a1 equals a2 equals 1, it's the convolution. It's integral from minus infinity to infinity, 1 over pi, the normalization constant, 1 over 1 plus t squared, 1 over pi, 1 over 1 plus x minus t squared dt. How do you evaluate something like this? Well, interestingly, I know how to evaluate stuff like this and related things like this using complex analysis. I do not know how to evaluate this elementarily using just real analysis. As a nice exercise, you could try to look and see what happens if we let x get very large. If we get x very large, can we get some idea of maybe what the tails look like? So as extra credit, analyze as much as you can the sums of two Cauchy. Maybe do experiments. Maybe do some theoretical calculations. If it's going to converge to a Cauchy, which one? Can you look at some numerics and guess which one it must be? Can you evaluate this integral? This is a Calc 2 integral. Unfortunately, most Calc 2 integrals cannot be done in closed form. Well, if it's supposed to be a Cauchy, you know which one. Maybe you can somehow take ratios and try to find a way to approach this. Anyways, I've got to go to the colloquium. 23 minutes, 54 seconds. Win a little